Hello, my name is Joanne. I'm going to introduce my term project for the course Computer Architecture 2025. So my term project topic is to optimize the QR code generation programs for my CPU. So my goal is going to optimize the provided reference code, which is the QR code generation, and optimize it with some assembly like RISC-V. And meaning is RV32I this format. So my after I've optimized the QR code, I need to make it run on my CPU, this hardware, and use the visual devices on my CPU to render the QR code so the user can scan the QR code pattern successfully and decode the correct strings. So now I'm going to introduce the details of this term project. And the first part is the for project source code link. There are two links. The first link is to run the QR code generation on RV32EMU. I use it to test the QR code generation code functionality and at the beginning process of this term project. And the second one is the target of this term project is to run the QR code generation on my CPU. Okay, now I'm going to introduce the background of QR code and showing the step-by-step of generating the QR code and the step for filling all the patterns on the QR code. And the first part of this QR code, this names means quick response code, and which means it will encode characters. Sometimes it's strings, and each character and can encode into one square symbol to represent all the data. And so the user can use their phone to scan the pattern and decode it into the original string. And the name means quick and response, so it can be scanned and quickly read. And the features of the QR code are the first one is the high capacity encoding of data. The QR code can represent four types of data, such as numeric 0 to 9 or alphanumeric ABC and some special characters and kanji, and the byte mode, which means one character is which means 1 byte. So for example, the H character, there are 40s in hexadecimal, so it can be encoded into the 8 bits, and each bit is units on the QR code. And 0 means white module, and 1 means black modules. And the second feature is the capacity of data is larger than traditional barcode. Before the QR code, there is one invention which is barcode. The barcode consists of several vertical lines, and each are different weights, and they are placed horizontally one by one. And QR code, you can store the data horizontally and vertically. And besides, you can read the QR code from any orientation. And you have to achieve this capability, you have to add 3 position detection patterns, which are also called finder patterns, and some specific location, such as the top left and top right and bottom left location. And with these 3 finder patterns, you can scan the QR code from any orientation. And besides some fixed patterns, the remaining parts are mainly the data area, which are our encoded string. And in data area, we consist of 2 kinds of data. The first one is the original encoded data, and the second part is the error correction part. The error correction part is used to generate the right decoded string, even though the QR code may be overlapped with some dirty things and be covered, so the scanner cannot easily to see the QR code patterns. So with the error corrections bit help, it can combine with the data code and generate the correct one. So now I'm going to first introduce about how to encode the QR code pattern. And before we started, I have to make a notice about the some names about like this module. The module means one element, one unit in the QR code, and the module you can think of it as the pixel, but it's not exactly like the pixel. It's elements and units, and in the QR code, one unit, one module is one color like black and white, and you can in byte mode you can see it as a binary 0 and 1, and one module means 0 or 1 and black and white, and with all these modules you can format only in QR code. So first, the QR code has several versions. They are ranged from version 1 to version 40, and the version 1 the width and height are 21 times 21, and when we increase one version, we will increase 4 modules on the height and width. So on the version 40, we have 177 times 177 modules. Okay. Now I'm going to introduce how we can fill the QR code step by step. And first, we will fill the QR code with some fixed function patterns. They are not related to the encoded data. They are just the rules we have to follow to build the QR code pattern. Then those function patterns are finder patterns, timing patterns, and separators and alignment patterns, etc. So there's the below example, I take version 2 as an example, which is 25 times 25 modules. And the first step is to add the finder pattern. The finder pattern, they are all the same. They are all 7 times 7 squared patterns, and they are put as top left, top right, and bottom left. And besides the finder pattern, we have some separators, and separators are located as near the finder pattern. They are surround the finder pattern with white modules like this. Each finder pattern has their own separators. After we add the separator and finder patterns, we need to add the alignment pattern. Here is the alignment pattern format. There are 5 times 5. And if we want to find out what coordinates the alignment pattern should put, we can go to see this alignment pattern location table to see the coordinates of this kind of alignment pattern. And take version 2 as an example. The center module coordinates is 6 and 18, so we can put 4 alignment patterns. Their middle coordinates are at 6 and 6, 6, 18, 18, 6, and 18, 18. So we can see on this picture we have 4 alignment patterns. Those 3 alignment patterns which are overlapped with the finder patterns, they are going to be omitted. So we only keep the last one, this first one alignment pattern on the bottom right. So here comes to the currently result. After this, we have to add some timing pattern. The timing pattern is one straight lines which are alternating dark and light modules. They are put between the separator, which is as 6 row and the 6 column. So we can add these 2 timing patterns. Okay, now I'm going to add the dark module and the reserved area. And the dark module is added at this corner, which is only one module and it is a black one. And the reserved area is the blue area in this picture. We have to reserve this area for now, and later it will be filled some data, which is our error correction formats and the mask formats information to show the technique we use on this QR code to let the scanner knows. Okay, and the next one is to place the data pin. It will introduce how we can place the real data, encoded data, onto the remaining part, which is the gray area in this pattern. And the rules are following the sequence like this picture. We have to follow the ray lines. First, we start on the bottom right area. We moving upward until we reach the top, and then we move to the next two columns, and we move downward until we reach to the bottom, and then we move forward upward, and repeat it again and again until we fill all the QR code. And when each time we move upward and downward, we fill the two columns, and the pattern is like this. When we moving upward, we are going to fill the modules from the bottom right, and then we fill the left one, and then we move upward right, and then we move left. And if we are moving downward, we are starting with the top right pattern, and we move left and moving down right, moving left, moving downward right. So each time we fill the two colors in a row. Okay. So if we encountering function patterns like we just filled previously, we just to skip the modules and find the next unused module. Okay, now here is the format and version information. This information are going to be put into the blue area. We said it before. And on these parts, we have to record some specific data like the error correction level. Error correction level, there are 4 kinds: L, M, Q, H. Their recovery percentage of data are different. The L level, which is 7%, and the H is 30%, which means it can recover more data which are more damaged QR code. So each level they use 2 binary bits to represent the level. So this part we will need to generate for 15 bits, because the blue area has 15 bits capacity. So we have to generate 15 bits to fill this blue area, to show we use which level and we use which max pattern. And the max pattern is going to, there are 8 max pattern, and max pattern is going to use after we construct the old QR code pattern. And the max pattern, they has 8 kinds, and the first one, the little mask, we need to consider this formula: the row and column, which are the coordinates of that module. If the row coordinate add column coordinates and mod 2 equal to 0, if the formula is correct, we need to switch the bits, which means if it is the dark module, we need to switch it to the to light module, which is white, right? So in our implementation, we only use max 0, this kind of mask, to generate different QR code. So if we use little mask, we need to fill the bits, which is 0, 0, 0. Each mask pattern is represented by 3 bits. So here is an example about these parts. So we can assume the label is L, and the mask pattern we use 5, for example. So the L, which is 0, 1, and the mask pattern 5, which is 1, 0, 1 in binary. So we can combine these two, and we have the first 5 bits. And we need to use these 5 bits to generate the error correction bit, which is 10 bits by Reed-Solomon error correction. So we need to do some math calculation, which is mainly the polynomial division, which are called Reed-Solomon error correction. So after this calculation, we can get the 10 bits we want, and we combined it with the first 5 bits, and now we can get the 15 bits totally. So here is the results. Here is the combined string. Then we need to fill the combined string followed by the order like this. We need to fill it into this blue area following by the numbered sequence on the blue modules, which is 0 to 14, and we need to fill it 2 times in different location blue area. And after this, we only need to fill the remaining part, which is our old data area. The other part is the fixed part, which to introduce the characteristic of this QR code. Okay, the next one is the data masking, and we previously said that data masking is going to switch the bits. So we in the formal QR code generation, we also need to add a new step, because it is called calculating penalties condition. In formal generation steps, we need to max the QR code 8 times, which with different 8 mask pattern, and after that we have to calculate the penalty score on less 8 kinds of results, and then we choose the penalty score which is the minimum one, and we conduct the less minimum one mask pattern until the final results of QR code. But in the implementation, we didn't do this calculating penalty score, and we just only use one mask pattern, which is 0. And after we fill all the QR code pattern, we have to add the quiet zone around the QR code, outside the QR code, which is 4 wise module wise, surrounding the QR code. And with this, the scanner can successfully scan the QR code. Okay, here I'm going to introduce the detailed steps to encode the input data. And now we take the input string as hello world as an example as our input data string. And we assume that our QR code version is version 2 and error correction level L. And here is the table that shows the different version and different error correction level, which consists of the character capacity of each mode. And starting to encode the data, we first need to set some bits before the encoding data. The first one is the mode indicator, and the mode indicator is used to show the scanner which encoding mode that we used. And here are the several modes, and we use alphanumeric mode and in this example. So in this mode, the mode indicator is 0010, which is 4 bits. And the second part is the character count, and the character count stores the length of the input string. And in our example, the hello world string is 11 characters, so the length is 11. And in this mode, the character count needs 9 bits to represent, so we just input the 11 in binary into this 9 bits area. So currently we got these 2 parts, and later we have to encode our string hello world, and we can following by this alphanumeric mode encoding table to encode the character into the decimal values. And in this mode, we have to do some calculation, and we need to follow these rules to calculate all the decimal value. And later we convert all decimal value into 11 bits binary value. And later we combine all these 11 bits value into our encoded data, which is yellow text here. Currently it represents the hello world in binary. And later we have to add the 4 0 bits as the terminator to indicates that our encoding data is ended. So, and besides the QR code version 2-L, the total number of data code words for this version and EC level is 34. So in the first part, in the data part, we need 34 code words, which will become 272 bits because each code word is 8 bits. So we have to pad in the current data into 272 bits, and our current data bits is only 78 bits. So we have to do some padding, and first padding is to pad 0, and this kind of padding is used in order to pad the all bits into multiple of 8. So we need to add 2 more 0 bits, which becomes 80 bits. And later we have to do some special padding. This kind of padding, they have the fixed padding types. And the padding type is 236 and 17 in decimal. So we need to repeatedly padding this kind of pattern until we reach the 272 bits in total. So later we can convert all these data bits into code words, and here we got 34 data code words, and these 34 data code words will become the coefficient of the message polynomial we need in the next part for generating the error correction bits. So we can fill all 34 code words into the coefficient of this polynomial. And later, after we prepare this, we can go to generate the error correction bits. Error correction bits in the theory is called Reed-Solomon error correction. The main concept of this error correction is just use polynomial long division, which means that we use message polynomial divided by a generator polynomial, and we collect the residual coefficient as our error correction bits. So here is a table that shows that how many coefficient in error correction or in residual that we need. And in our example, the version 2-L, the error correction code words we need is 10. So we need 10 coefficient for the remainder part. But the arithmetic in the polynomial long division isn't the same as the real number field. It uses a special arithmetic number field to represent the mathematical operation, and this field is called the Galois field. And in Galois field, which is special because, for example, in Galois field 2 to the power of 8, which is GF2 256, and all the number in this field are between 0 to 255. And in this field, all of the mathematical operation will result in the same field. So it didn't need more bits to store the number in this field. It just need 8 bits for each number. So because of this special characteristic, the mathematical operation isn't the same as the real number one. So for example, in this field, when we do the addition and subtraction, they are the same, and they are conducted by doing exclusive OR. And if we want to do the multiplication, we have to be careful that the multiplication result might exceed the 255. So we have to do the modulo to let it stay in that range. And how to let the number to stay in that range is conducted by mod 255. in this field, it is really conducted by doing XQCR with 285 in decimal to bring the number back to the range. So here I'm going to introduce the multiplication flow. And here it takes a way to do it by looking up a table here, which is the quickest one to finish the multiplication rather than doing the real multiplication. But be careful of the addition and subtraction, which need to follow the Galois-Field rules. So here we can introduce the multiplication flow. And before I continue, I need to make a notice about that every number in Galois-Field can be represented as 2 to the power of n. So if we want to do the multiplication like a times b, a can be represented as 2 to the power of I, and b can be represented to 2 to the power of j. And we need to do these two numbers multiplication, so we can first get the exponent value I and j by looking up the log table. So we got I and j, and we can just easily do I plus j addition and the mod 255 if it exceeds this value. So we got the 2 to the power of n in result. And later we have to use anti-log table, anti-log n, to get the real value that represents converted back. And so we got the final result in this field. So this kind of multiplication, by using lookup table, we have to look up the anti-log table and log table each for one time, and we can get a result. We don't have to really do the complicated multiplication. We just need to do exponent addition and some modulo steps to get the results. So this one is the quickest one to finish, to complete the multiplication. And so we can go back to the Reed-Solomon error correction. So in Reed-Solomon error correction, we need polynomial long division. So we need to prepare the dividend and divisor. And dividend is our messenger polynomial, which is our data code words, and the divisor is the generator polynomial. You can use a tool to generate it, and because we need 10 code words in residual, so we generate a generator polynomial which consists of 11 coefficients, which starts from s to the power of 10 to s to the power of 0. And here is our generator polynomial. And then we perform the long division by message polynomial is divided by the generator polynomial. And so we can see the division steps showing here. So it's similar as the long division steps. So we first need to multiply generator polynomial by 32, so that the first coefficient can be the same as the messenger polynomial one. So here we can do the subtraction, so we can eliminate the first term. So but have to be remembered that the multiplication and the addition and subtraction is special. We have to follow the rules that I introduced before. So here we can repeat these steps to multiply the first term's coefficient and do the subtraction. So here we can see the subtraction is using XQCR to really conduct these steps. So after we repeat steps 1 and steps 2 repeatedly until our remainder is consists of 10 coefficient, which is 10 code words that we need for error correction bits. So the final remainder will become here this kind of polynomial. So we got a 10 coefficients starting with 240 to 134. So we finish all the calculation. We can list all the data codes like this one, like this table. And we got all 44 code words we need for this table, and which consists of our error correction and our hello world string data. And we just list all these code words into a table, and we convert each code word into 8 bits binary, and each bit represents the module's color in the QR code. So we just fill all the bits into the QR code for their related color into the bits, and place the data bit following by the rule that I introduced before to fill all the remaining gray module to successfully fill all the QR code pattern. And after placing all the data bits and add the quiet zone, we can get the correct one QR code for the scanner to decode the string back. Okay, here now I'm going to introduce the detail of my implementation on QR code generation. And first, here is the notification about the characteristic my QR code supports. The first one is the version. I only support version 123, and I use the error correction mode, which is L. And the encoding mode is byte mode, and which can encode the character into 8 bits. And my character capacities for each version is listed like this. And in version 1, you can encode it up to 17 characters, and in version 2, you can encode it into 32 characters, and in version 3, you can encode it into 53 characters. And I use the math pattern, which is 01, the first one. And right now I have to introduce the reproduction steps of my QR code. And here is another notification about my experience setup for the cycle count. In the later introduction, I will show the performance of my QR code generation. So I will do some experiments, and here is my experiment setup. And I only use QR code version 3, which is 29 times 29 modules, and also use LL correction mode, and I use Leroy's math pattern. And for the testing input string in RV32EMU, I use this input string to test, and in my CPU, I use this one. And here is the reproduction step for the user if you want to generate your QR code. And in RV32EMU, you have to clone this repository first, and go inside this folder QR code generator, and just type making or run. It will show the QR code rendering on your terminal. And if you want to change the QR code input string, you have to modify the source code about QR code generator.c file, and just type making or run again. It will see the different QR code result. And in my CPU, the step is also go first clone this repository first, and go inside and check out this feature QR code branch, because my developments about QR code are all on this branch. So you have to check out to this branch. You will get the QR code source code and some modification about this project. So next is going to compile and simulate the QR code, and use the VGA device to render the QR code. First, going to the second version in my CPU, which is MMIO checklist folder, and just type make demo QR code qr_str equal to your custom string. I modify the make file that it can input the custom string, and just dynamically to render different kind of QR code. And if you want to use the default string, you don't have to add QRSTR. You just type make demo QR code. And the default string is this one. It's the same as the experiment one. Okay, next one is if you want to compile the code from the source. Source is stored in this folder CSRC. You can type this makefile make -c CSRC clean QR code bj.smbin and input your string, which is the same as the next one. And must quote a string like this, one single quote and one double quote. And finally, just remember to update it. It will copy the executable file into the source file. Therefore, you can make demo QR code to render the QR code you will just update. Here I'm going to show the simple example of demo this QR code generation process. First of all, you have to go inside this folder to MMR trap and just type the command I introduced previously to first make demo QR code and input your custom string QRSTR equal to, and just input your string here. I input youtube.com and just hit the enter. And you will start it to make a QR code generation. Here we can see the visual display from my CPU. You will see a complete QR code pattern, and you can scan it to your phone to check if it's successful and if it's the same as your input string, and just hit the escape key to close the window. And in my code, I also let it can calculate the performance of cycles count, and I will print it out by UART peripherals, and the result is 222589. Each character will be repeated, printed out 4 times. So if you want to read this number, you have to read 1 character and skip 3 character to read next one. So here's the cycle count is 222589. So here is the small demo of my QR code. Okay, now I'm going to introduce the implementation of a QR code in this term project. First of all, I implement this QR code generation and test the optimization on RV32EMU, this emulator. I first use it because I want to make sure my QR code generator is correct, so my phone can scan it correctly and get a correct decoded string. So my reference code, which is this QR123.c, and it optimized using Amazon assembly. In this function are Reed-Solomon multiplication. So my optimization number 1 is also optimize this function by implementing in RISC-V assembly. So this function, it has several methods to implement it. The first one is using the log anti-log lookup table to do the multiplication. So here this method is the quickest one, but it needs storage to store the tables. And the second one is use C version, and you just iterative the multiplication steps. And in this function, you can see here is one here formula is going to shift right the lead variable for 7 bits and times with 1D in hexadecimal. It's used because it need to check if the variable D to prevent it from existing 255 in Galois field. So it is character for modulized 255. So I implemented with RISC-V assembly, just translate it into my RISC-V assembly code. So I can definition my optimization into several versions to enable it in order to introduce them in performance. Okay, so the first one, version 0 is the lookup table version is the fastest one, and the version 1 is the original C code, which make it run on RV32EMU, and it is the iterative GF multiplication. And in version 2 prime is just translate this C version into RISC-V assembly version. And in version 2, I optimize some multiplication, and I by eliminate the unnecessary multiplication loop, like this one is the multiplication in this function. There are two sides, here and here, and I noticed that if the lead variable is only 8 bits in this galois field. So if you shift right the lead variable in for 7 bits, you will only get the most significant bits in the variable. So it must be 1 or 0. So I make it to just decide if this term is 0 or 1 to get a different value. If it is 0, this term will become 0. If it is 1, it will become 1D in hexadecimal. And here is also the same thing. In this term, if you end this term in with 1, you will only get 1 or 0. So it is 1 times x or 0 times x. So this is the unnecessary multiplication to do. So you can just remove it just to determine this term and this term, to determine if they are 0 or 1 to decide the result value. So in version 2, I optimize this kind of unnecessary multiplication into version 2. So I'm going to show the performance statistic about these three versions. In this statistic count in 0, 1, 2, I can show the cycle count and instruction count. They are the same. And in version 0 is lookup table. For C version, it is the less cycle count. This is the cycle count. And version 1 is iterative multiplication on C, and it has the most cycle count. And in 2 prime version, it is translated into RISC-V assembly but not optimized at all. So it will become this kind of cycle count less than C version but higher than version 2. So version 2 compared to version 1, it can see that using the assembly code, it can reduce almost 100,000 cycle counts. So it can see optimization by using assembly code is successful. Here I'm going to introduce the optimization number 2 and number 3. And in optimization number 2, I want to decrease the usage of multiplication, divide, and because in assembly I only compile it with RV32i without the M extension, so I need to prevent it using the M extension operation, so I can replace them with AND operation or shift left, shift right. And by doing this, I can decrease 1,701 cycles instruction count. And here is the difference before after the optimization. You can see I replace mode 2 into AND with 1, mode A with N7, and just we use the multiplication and divide into shift left and shift right. And in optimization number 3, I optimize this Reed-Solomon function call. And in this Reed-Solomon function call is going to conduct the polynomial long division steps. So I first check this source code, which is written in C. I noticed that there is one line is repeatedly moved, and I think is unnecessary, which is this line. This is a residual array, and which contains of the coefficient of the residual polynomial. And in each loop, I've noticed that you have to repeatedly to shift the residual number into the previous one. And I think this is unnecessary and waste of time. So I want to make this residual array into a ring buffer. So I only need to store one variable, which is offset, to act as the beginning index of this residual polynomial. So I only have to update the index, this offset, to let it point to the beginning coefficient. And remember to rewind the offset if the offset exceeds the length of the residual polynomial. So here is the optimization results, which you can see like this, and you can see a new variable offset, and each tiny offset means the first coefficient of this residual. So you will also all calculate the factor with this residual first one of coefficient. And in here it is going to make sure the index now existing the degree, which is the maximum length of this residual polynomial. And in the end of this function, you have to remember to rotate the buffer back to let the offset being 0, which copy all the residual and copy the residual back into the residual array, which is the residual 0 means the first one. So you have to copy back, and you just need to organize it. In the end, you don't have to organize the residual in every single times in the loop, so it can save a lot of cycle count. And by doing this, it can decrease the 2,665 cycle count and instruction count. So here is the statistical result with these two new optimization. It can be called 3N and 3B. And 3A is combined with the lookup table, and in 3B you use the iterative Reed-Solomon multiplication RISC-V version. And you can compare the 3A version with version 0. You can see it also decrease the cycle count. And compare 3B to version 2. You can see it also decrease the cycle count. So which means the best version currently is 3A or 3B. Here is the best one. So in my repository, GitHub repository, I already chose it to use 3B version as a default demo situation. Okay, after I successfully generate the QR code in RV32EMU, I tried to move the source code into MyCPU to test it with my target simulator, target hardware. And I test on second version MMIO trap in my CPU. So I first check out a new branch feature QR code to do the development about QR code in this project, and I go into the source file folder and generate these three QR code related files, which is QR code gen.c, which is a source code to generate the QR code bitmaps, and the QR code vj.c is going to to fill the frame buffer in QR code, which is only one frame, to fill the frame buffer with the data color to the VGA device to render the QR code pattern by my CPU. And I adapted it from neoncat.c file. I look at this file to see how it fill the color and how it use the palettes to define the color and how it declare the frame and how to fill the frame buffer. And so it is a VGA.c is the main program to use the VGA device. So it will get the results for generating QR code and use it to show it with the VGA device. And this .h file is the header file. You will define some constant variable and some shared variable between these two files. So here you can compile with this command and run it with make demo QR code to simulate this rendering. And also in debug situation, I can use Trisol scalar tester to print out or compare the data I stored into memory when I generate a QR code or I render it to VGA, so I can see the possible wrong situation by this Trisol test. So I mainly write the test code on the CPU test.scalar code, and you will run the QR code as executable file. And you just need to type this command to run this test. And here is the example of the correct QR code pattern, and it will show the VGA display window from my CPU. Okay, now before I successfully generate a QR code, I encountered some bug when I just removed the QR code which is successfully running on RV32 EMU, but in my CPU it is wrong. So I need to fix this bug. So the first bug is no matter what string I change, I noticed that it always give me the same QR code pattern. So I think the string variable isn't quite right. So I found the problem is that I declare the string like this, and which makes the string is a pointer and it will store in data section, but the value of this string is AAAA. It will become a string literal. It will be stored in the read-only data section. But in my Mac file, I only copy the text parts and data parts into the final executable file. So I change it to declare the string like this. I declare string to an array, and its value will be stayed in this data section. So therefore, my QR code generator can get the correct one string. So here is the change. And the number 2 bug is happening when I apply optimization 1 and 2. The optimization 0 is the lookup table for the Reed-Solomon multiplication, but in 1 and 2 it will be wrong results. So I'm convinced that the problem is come into the multiplication function. But in the end, I find that I use the Trisol test to test the multiplication result from all 825 multiplication, and I see all multiplication are passed. They are all correct. So which made me very confused at that time. So now I think I knew that multiplication is correct. So the problem may in this Reed-Solomon function. So I also use Trisol test to print out all this array to see their data, check their data if the same as I input to them in this array. There is their correct one data. So I have to check if they are the same as this array. So in optimization derivative, they are all correct for the gem array. But in optimize 1 and 2 layer, the last two data isn't correct. So I find out the problem. So I try to declare this array before I use it in resolvement, and I avoided to declare the array like static counts. I only declare it with uint at t to prevent the problem of real data or data session, like bug fix 1. So here is the difference. When I optimize it, I fix this bug, and after I fix bug 1 and 2, I can render the QR code successful with my expected results for each optimization. So after I successfully render the QR code on my CPU, I can measure the performance to test my optimization results. So I can make sure the cycle counts in 2mml trap version. So how can I get the cycle count data? So I noticed that in CSR.scalar there is a 2 register, which is cycle low and cycle high, and they are each are 32 bits. And so I can use this function, read my cycle, read m cycle and read m cycle high with this CSR assembly code to get the cycle count value, and I combine low and high into a final cycle count number, and I measure the difference before and after calling the function generate QR code. And I have to print out the cycle count results, right? So I use UART put C function to it can print out the character one by one by using UART peripherals, and I can use it to print out my cycle count. But in this version, I only can print out cycle count, print out the character like this. Every character will be repeated for 4 times, so I have to read it by myself to see the cycle count, and I skip the unused character. So here is the cycle count table, and in this results, the ranking from large to small is consistent with the statistics in the RV32 EMU test. So in here I can see the best one is also the 3A version, which use lookup table and some new optimization. In my default choice in GitHub repository, I use 3B version 1. So here comes to the end of this illustrative video. So in this term project, I can learn how to generate a QR code, to learn its background and learn the process of building the QR code steps by steps. And I can also optimize the original C code with RISC-V assembly, and I can learn how to analyze the optimized performance. And later I can run and render the QR code through visual device in my CPU, and the most importantly, I can find the bug and I can fix it. So in my conclusion, in this term project can successfully optimize the QR code generation code by making it more suitable for RV32i situation, and I can prove the optimized performance by recording the cycle count difference and make the QR code run and render the QR code through visual device in my CPU. So thanks for your listening for this video.